amplitude reaching the largest possible length of the pendulum. So the least accurate point would be like 4.
Yeah, I'll try to get you.
Let's make this a little smaller. Here we go. All right, cool. Move back. Oh yeah, so let's do. So we were looking at pendulums, figured out we could predict and measure and then get some kind of error between like time period. Time period's usually a little easier to measure than something like frequency, even though they're both the same kind of number, the inverse of each other. But usually easier to like watch a time period than it is to figure out like number of cycles per number of cycles per second, something like that. And we had measurements there. What was time period for that long, for the big pendulum? Didn't we figure out it was like
Yeah, it was like 5.7.
5.7?
Yeah, I had between 5.7 and 5.8. So 5.7. It hit the wall at one point. I think it was between these two.
I mean, it hit the wall at there.
Okay, we were not under ideal conditions.
T was 5.7. We can take that.
Yeah.
5.7. And that was, let's see, we can say 2 pi over root G over L. What was L? How long was this thing?
Oh, so we can solve for 3 stories. Oh, how long is that whole story? I mean,
But it's not to the top of the story, it's to the top of the window.
We might be able to find like a building plan.
Yeah, I measured it, but I want to know how close we got. Because I like brought it down the hallway and counted how many 1 foot squares there were and then measured the last few inches. Like typical dumb professor. We need the height, but we got the length instead.
I think they're the same.
So what's L? If this is 5.7 equals, there's only one unknown, right? Just.
Oh yeah.
So what is L?
No, get to the calculator. Don't you just like move the square root to the left, divide by 2 pi over 5.7, and then you take the square root of that, and then you do
Yeah.
that over G.
0.1 meters?
How much?
No.
8.1. Did you use 9.81 for G? Okay. What was it? 8.1? 8.1.
I thought you said 0.1 meters. Like
Something like that.
Yes.
So what is 8.1 in feet? Because I got it in feet. What? Oh, meter.
26.57 feet.
26.5.
Which is about right for half of 2.5 stars.
26.57.
26.57.
Yeah.
All right.
Yeah, it's about 2.5.
2.5 what?
Stories,
How tall
yeah.
is how tall is the story?
10 feet. Building
Oh,
code?
yeah.
I don't know.
And then
Jarvis, how tall is the story?
Depends on how tall the ceilings are.
I know, I feel like it's unique to each building. 10 to 14 feet according to Google AI overview. However, this varies widely for just
26.7 inches. So when I measured it down the hallway, I got 26 feet 8 inches. Pretty darn good, right?
Yeah. So
Yeah.
what was our L approximation?
We approximated 26 feet 7 inches because 0.57 multiplied by 12 inches ends up being like 7 inches. So we were like here we were kind of doing the opposite calculation, right? Like measure time period, can we figure out what this structure looks like? And we hit the wall. There was wind, like there were a lot of other things happening, but time period, like natural frequency, it's called natural frequency because it's such a stable value. Like it's pretty easy to measure most of the time. Like sometimes there's other stuff that gets in the way, but we're doing pretty well. Within 1 inch is pretty good for even all those other things happening. And me kind of hanging it out the window with a hand. I wasn't even watching. This was like a blind test. I was just trusting you to do it.
And we can find the actual period since you know the actual length, and we can see how far out.
Yep. Yeah, what does that end up being? Over. Yeah, 26 plus. Yeah, 5.717, and we got 5.7. So within 17 milliseconds.
I'll take it.
Yeah, it's really good. It gets so the longer the pendulum, the less the unknown length really affects it, right?
Why?
As it keeps getting longer, because we have that like square root of G over L in the denominator. So, well, I guess root L is over there, but whenever you have that square root, like this, the propagation of error is not as big as the length keeps getting bigger.
Okay, I wrote about that in my project. I was going to ask you that during class. So, like,
Oh yeah.
but so we have the linear one, and that one's whatever value we calculate is going to be precise. It's relative to the linear one because you're just multiplying those two things or dividing whatever. But for the nonlinear like equation, you have like cosine or sine and stuff, and I think
Yeah,
and
for
the way Python runs that, depending on how many steps you have, you might lose some data along the way in between steps. Although it would probably end up being negligible. I was
You mean
just
this
thinking
here?
I was just thinking about it. Like,
Yeah.
like depending on the number of steps, I think you lose something in the sine data, like because there's a ton of decimal points. But overall, it's negligible. I was just curious what you think.
Yeah, so there's kind of two competing errors in whenever you start using here our numerical solution that we're getting, we have an exact differential equation. It's nonlinear, but it is the exact. So the bigger the angle, it's not that it's always a G over L acceleration, it's really sine of the angle times G over L. So that part's exact, but whenever you tell the computer to integrate for you, there's something called like truncation error where during the integration process, the same way that we said sine theta is theta, there's an approximation that every time step that sine theta is going to be like, maybe it's a quadratic equation, or maybe it's a fifth order polynomial, and we're integrating that over that. So that one, there's truncation error there. This is more like computational mechanics stuff. But as you keep making time steps smaller, that truncation error disappears because it becomes exact. Because if you look at any function on a small enough period, it looks like a straight line, unless it's really nonlinear, like the sine of, what was that? I think it's like sine of x cubed over x or something. Like if you get like real weird functions that change a lot, then you end up with other errors. So truncation error, that one gets taken care of by the algorithm of solve IVP. It like tries to converge and get you a good solution. But then there's also round off error in the fact that when you store a number in a computer, you have to approximate that number because you only have 64 bits to say, all right, these are all the decimals in my number. But those errors, really it's like 10 to the negative 16. So it's so much smaller than most stuff that we're dealing with. Unless you're talking about like, I don't know, planet orbital mechanics of like, all right, let me look at 3 decades into the future. Now it starts adding up. That was a long answer for a short question. Yeah. Like, is this error there? Like, yes, but also no. Yeah, but actually no. Yeah. Yeah, so like one of the questions is kind of which one is more accurate? And that was a long answer from me because I have a lot of background in like both numerical methods and like physics and engineering and all of that. But it's okay to just say like, okay, we showed in class, like we measured time periods and then we predicted time periods. That's an accurate answer. And so this, maybe my linear solution is really accurate to within, at least most of the time we figured out like less than 2% or 5%. So that's a very accurate solution. We didn't try large time period. We didn't try like large angles and measure those time periods, but that's all right. You can always go to the playground and try like swinging on a swing.
But generally the numerical solution will always be more accurate, right? Unless you're talking about like really small scale stuff.
We have to keep back to the value side.
What's that?
But it's the actual values, the numerical.
Yeah, that's what I'm saying. The numerical one's more accurate than the linear.
Yeah.
Shouldn't that always be really true?
Is the numerical more accurate than the linear? So as we get to small angles, there shouldn't be a difference. And the differences that we see are like computational errors. So if you actually have small angles, so right now this is looking at like 60 degrees. What was the number that we came up with? 15? 15 was our small angle cutoff. I like 30, but 15's good. 15's like factor of safety, right? It's a cautious class. Actually, let's go back up. Let's change L. Instead of 5 meters, we want, oh yeah, what did we figure out? 8.1 meters, our 3-story pendulum. Doesn't really change like what was going on, but it changes. Now our x-axis is a lot longer because now we're looking at 2 full swings from the 3rd floor. And here, when I look at like 15 plus minus 15 swinging, there's really no visual difference. But technically there is a difference, right? There's always a difference. You can't, unless you're actually calculating like the same thing. So we'll take these two and subtract one from the other. So initially, at time 0, they both started in the same spot, but as time goes on, we start seeing some difference. Not big though. We can't see it in a plot of theta, but 0.6 up to 0.6 degrees by the second time period. And that's where we start seeing like numerical error. Yeah.
So what is that graph showing us?
This is the difference between linear and nonlinear, just taking the two values and subtracting them. So right now it went from 15, both of them went 15, negative 15, back up to 15. And if we subtract the two values, now we can see that after one time period, they're 0.2 degrees different, or 0.2, yeah, 0.2 degrees. Yeah. Small, pretty small here. All right, so then I think last thing we talked about a little bit, but like what else could you calculate? And what did you try to like plot anything different? Yeah.
I didn't plot anything different, but like I made two observations, kind of discussed them. The first being like you could compare the two periods between the solutions.
Yep.
I put the equations as like looking at them for the periods like t for linear t equals mg, and for numerical t equals mg cosine theta.
Yeah, and that's a great way for like the second question of saying like, hey, based on the plot, the information that I have these two predictions for linear and a nonlinear pendulum. Let me calculate period and compare that to the graphs that I have. Because we didn't, in these graphs, like, I guess, let me rerun it because we did. Now we're down at 15 degrees. So in here, there's no difference between the time, at least no measurable difference in the time period. So they're both 5.7 seconds. What did we figure out? 5.7, yeah. Just shy of 6, which matches up with our measurement and our prediction that way.
And the other thing I was talking about was conservation of energy.
Okay.
I wasn't entirely sure how to plot it, but I feel like the numerical model should be close. I talked a little bit about round off error.
Okay.
But the linear one would probably be similarly just like, actually linear one would show complete conservation of energy.
Okay.
Because you don't have to worry about like any loss of data. It might not be like perfectly accurate, but it would never show any loss of energy. But like sometimes with round off error, with the numerical one, you could
Yeah.
lose, but not actually.
And so this is kind of a segue, like module 4 is all about like energy and momentum methods. So what is our conservation of energy for a pendulum? First off, what's the equation for conservation of energy? I know everybody has been doing thermo.
It's just like the total energy, is it kinetic?
Total energy, yeah. Total energy, is it changing for this case? No. There's no work in.
There's no change in total
There's
energy.
no change in internal energies.
There's no feedback.
What are you talking about? Yeah.
So like E equals a constant. And what are the things that make up the energy of this dynamic system?
We have like kinetic and potential energy.
Kinetic potential, yep.
Internal energy is not really a thing.
So T plus V, so I don't know. Thermo, do you use KE for kinetic? All right, here we use T just because. And then V, do you use PE for, yeah, okay. Here we're gonna use V just because we don't have to worry about volume flow rates. So V is potential energy.
T is kinetic.
T is kinetic.
Yeah, sorry. I don't know why, but like that's
Decided that.
I don't know. I want to create like a universal list of variables for at least like an engineering program of like let's all agree that v is always velocity or something, you know, like little v is always velocity, not well sometimes it's specific volume. It's like
It's a squiggle.
yeah.
But
But
no,
anyway.
little v is specific volume.
No, no,
It's a
no.
squiggle.
Yeah,
Yeah, it's a squiggle V.
squiggle v, yeah, that one.
Italicized v.
Okay, so what is kinetic energy for anything here? Do we need to worry about rotation?
No, it's not spinning.
It's not spinning. At least we're ignoring
Not like-
if it's
like
spinning.
time
Not relative to.
Yeah. Okay. So what's kinetic energy then?
Just 1/2 mass times the velocity.
1/2 and v squared. Cool. What is our potential energy here?
Isn't it just the height times the mass?
Height times mass, something like that.
MGH.
NGH.
Yeah, great.
Cool. All right. Now we need v and h in term, because really what we're calculating is angle. So how fast is this thing moving at a given angle or angular velocity?
Get out of the kitchen.
So if it's up here and it's kind of moving down that way, and it's here at length L, how fast is it moving?
Well, you can do. What you mean? How fast is it moving? Or?
Mm-hmm. Yeah, what's the speed of the pendulum? Because that's what we need, right? Speed squared.
I was thinking of the V term.
Yeah, V, right?
Or I was thinking capital V. MG.
The volume?
MG.
Oh, okay. That, yeah, big V. Oh, MGH? All right, so
Yeah,
what's
I was thinking
MGH?
about
That one's fine.
It's like MGH, we know MG, and H is going to be like, imagine H is the distance from the ground to, I guess, like the hinge
Okay.
of the pendulum.
Yeah.
So it should be like MG, and then the H value should be like that H minus. Sine or
Why
cosine?
is that on the x-axis?
Because it's what we decided.
Should it be sine?
Why is it x-axis?
Sine theta.
I like to, if I'm measuring an angle, I always put the x-axis as my zero angle. If you don't like that, you can do it your way. You can rotate it, but it's heresy and you're crazy. No, you can do it that. You can change like how the angles are. It's just whenever I put the x-axis, if the x-axis is theta equals 0, then I can always use the equation that x position is L cosine theta, y is always L sine theta. And then I'll figure out after that fact of like where I want to put them. But that's me. Again, you can do it your way. So you want to say like this is H? So it doesn't have like it never goes to 0
I mean,
MG?
the way I was thinking about it, I guess it doesn't matter how you portray it, but I was thinking H is just the distance from the ground, so
Mhm.
x equals 0, to the pin at the top where the pendulum is hanging from, and you could express that as just like H. Oh, I guess it's confusing because H is already in the equation, but I'm thinking H is going to be your height value is going to be from the ground to the hinge minus
Ground.
sine L sine theta.
Well, the rope of the pendulum
L cosine.
never goes to the ground. It like isn't.
Yeah, but it changes
Okay.
with mass.
Completely touch the ground, so.
But numerically, we could consider it as height 0.
Yeah.
Oh, I was on the mic train. I just realized. Yeah.
So we want to say,
I was on the same. I was in the same vein of thinking as you with like the.
So I'd say like to me, H equals 0 is when the pendulum is like vertical, so the bottom.
What does it matter? I mean, what I said, I don't think what I said changes. Like you just do the height, like the height from the ground to the hinge
Yeah.
minus the sine L sine theta.
Well, no, that way, we don't have an H term when it's perfectly vertical. If we
That's
measure it,
potential energy of
Yeah.
0. Because you can always say, you can set for H and for any, not for any potential energy, but like for springs, there's always some like 0. So if we want to think about this as a spring, there's some unstretched theta where when it's sitting there, that's when we have no potential energy.
Isn't there always?
yes, but
Shouldn't there always be gravitational potential energy in the pendulum?
Well, so the main thing, energy, the only thing that matters with energy is differences. So whether we say, like we could say that the hinge, like where it's mounted, is potential energy equals 0, and now it's always negative energies. Because we always have like a negative MGH. But we're going to be looking at positive differences as we go from whatever, -2 to -3. End up with an extra 1 unit of MGH, of MG, sorry. That one's kind of weird, but
don't you just want to express V in terms of theta?
yes.
So
Yeah.
you just need to change the H term to something with theta. Don't you?
Yep.
I don't understand why you can't just do L sine theta.
L sine theta? You can do that.
The vertical component.
So if we say that
But that
H
describes where
equals L sine theta, that's describing this distance. So it would be a negative, because we're saying like when it's 0, it's at the top. Or wait, not sine, cosine.
Oh yeah, it's cosine theta.
I'm like, wait, like where did that come from? Cosine. But yeah, same idea. Like we're taking that triangle, just get that horizontal. Or we can say that it's L minus L cosine. Then we end up in the same exact spot. Like this one, if this is H equals 0 down here, L minus L cosine theta. And in terms of like potential energy, there's no real difference in how you do it. The only nice part is that now you'll have a minimum that is 0 when you plot it. But all right, so let's replace this with MGL. I'm gonna leave it as that 1 minus cosine theta, just so we can see it. All right, so now how fast are we going? How fast does this thing move? What coordinate system are we using?
radially, like
Polar.
Yeah, polar coordinates. So,
Polar bears are scary, so polar coordinates.
yep, all right, that's fine. Just the first Google result. We can always go to the textbook and look it up, but maybe you don't always have the textbook, so Google it. What do we have? Is R changing? Is our radius changing?
No.
All right, so that one's 0, right?
Yes.
So that term's 0. So velocity is now R d theta dt. And what's R?
The length. It's L.
Length. Yep.
So L theta dot.
Yeah. So V is L theta dot.
Squared.
And that's always, it's always the same speed. Like L theta dot is always describing speed.
Okay.
So now we've got L theta dot squared. Cool.
And this is just for the numerical solution?
No, this is describing, I mean, this is describing like kinetic and potential energy for both of them. for the linear solution, technically we don't have, since it's linear, then we should have like a 1/2 mgh squared kind of thing rather than a cosine term, but it's all right. We'll just try it this way, right? Rather than doing a Taylor series expansion of cosine theta and then look at the squared term. All right, so the things that we need are theta. So let's grab like these two things. And we need d theta dt, right? And I'm gonna leave it as like radians, because do all your math in radians. It's better that way. Let's just give it a mass. Let's say it's 1 kilogram.
Yes, like you're doing too much.
It's just 3 questions. It's also double spaced and it pictures. There's not as much as that.
It's too much.
So I'm creating like a nonlinear v and then a linear v just based on how I calculated theta. So SOL y0 is theta, and then theta is my linear answer. So now T one half times M times L squared times d theta squared. And now I can look at like what happens with kinetic energy and potential energy. So blue is going to be, in this case, potential. So it starts off at high potential energy and then goes down to low. That's where I have max kinetic energy. Why is it happening so fast? Why isn't it the same time period though? Shouldn't it have the same frequency? What happens?
Well, as one goes up, like the other goes down. So
Yeah.
at the top, when the mass is at the top of the pendulum swing, it's going to be all potential, no kinetic.
Yeah.
And at the bottom, there's going to be no potential, but all kinetic. So they're like inverse of each other.
Yeah. Yeah. So, but why is it happening?
Can you show the equation?
Like we only have 2 time periods here, but down here it looks like we have 4, 8. Does that make sense? Or did I do something wrong?
Can you go to the equation?
Yeah. Let's scroll up. Yeah, I have 1, 2, 3, 4 peaks of kinetic energy. Does that make sense that we have that our position goes through 2 peaks, but kinetic energy is doing 4?
So if you have 2 peaks of,
It's like it's maximized at like both sides, but then it passes through that state twice and it's like
Yeah. So you end up with like symmetry, that everything that happened over here is also happening over there. But because it's energy, it doesn't really matter what direction you're moving. Like, speed is speed, forward, backward. It's all kinetic energy. Oh yeah. So here, if you want to see, remember we were talking about like where to put that, or I guess I could say 0 minus, right? Where do we put the h equals 0? All it does is change the offset of where your potential energy is. So it shifts it up to say that it's never the same like magnitude of kinetic energy, which, yeah, again, it doesn't really matter because we only care about differences, but it looks better when they're both like closer to each other. And it's like, yes, 0 potential energy is maximum kinetic energy.
Why is in your equation the linear solution for V have a cosine in it?
I'm missing a cosine?
No, why does it have?
Oh, why does it have it?
Yeah. Because I thought we were supposed to.
I was just using like the actual diagram, rather than integrating the MGL sine theta, and rather than integrating MGL theta, because that would be the other way. Oh my god, driving me crazy. So F equals like if you actually want to like figure out like what is the linear potential energy, it's the integral of that, because really the our force for the full term is MGL cosine theta, or MGL cosine theta, integrate, now we have negative MGL sine theta. So if you want to compare linear and linear value, then you end up with same thing as a spring, like spring constant kx, integrate that, now you have 1/2 kx squared. Here our k term is MGL. But I was just leaving it just for funsies. And then for nonlinear, we should see the same thing. And sure enough, we do. At least it looks like the same thing. So then the fun part is if I add kinetic and potential energy, what should I see at every step in time? Should be a flat line, right? Nothing changing. What do I actually see?
It's basically a flat line. Because
yeah.
Is there a Python command to scale your axes?
Yeah, if you want to say, like change the y limb, we could go like 2.5 to 2.8, something like that. If you want to just like zoom out a little bit.
Can you set its increments? Like say increment by 1,
What do you want to increment?
I don't know. I was just
Yeah,
curious.
but probably. The answer is probably yes. It's just sometimes it's like, yeah, now we just need 10 more lines of code. Other times it's like, oh yeah, there's a function for that. What? All right, so blue line is nonlinear. That one, there's some error, but for the most part, it's always like 2.71. Like that's just how much it is. What the heck's happening with our linear solution? Why is that one? It doesn't look constant, right? Like something is changing. Even we're at a small angle, like we're using small angle. We're getting the right time period. We showed that yes, time period is right, but something's off. It's weird, right? I mean, if you want, you can do. What if I do change it to that MGL theta squared over 2? Is it going to change?
Wait, what'd you do?
So like you were saying in the beginning of like, why do we have a cosine for a linear problem? Well,
You got rid of it?
if we change that to MGL theta squared over 2, where it's actually, since we said it's a linear function, then it should have a parabolic potential energy, not a cosine potential energy. And like negative cosine at the bottom kind of looks like a parabola, but it's not exactly a parabola. So the bigger the angle, the bigger the error we have. Yeah, anyway. But there's offset in the total energy, even a little bit. Not a big deal, but
they're both like approximately straight lines. So the
But
difference is actually fine.
yeah, exactly. Yeah, the difference is what. Cool. Anyway, so that's one of the things. So if you like that, that would be a great plot to add. Of like, hey, let me find kinetic and potential energy, compare, and then now I have a plot between those two. Another one. Like we could calculate what is the tension in the cord, and compare like what is tension for linear versus nonlinear. Have you seen that video of like the group? I forget, maybe like 8 people that tried to build like a giant swing to jump off of a bridge. Almost like bungee jumping, but they wanted to like swing. No?
I've never seen something similar.
What happened? Yeah. I think disaster would be a good way. No. This one. Yeah, that's the one. So it was like a whole bunch of, it'll catch up in a second. Whole bunch of people that wanted to like have an extreme kind of bungee jumping, like, hey, let's like do it real quick. We'll jump off this bridge and swing down. And they calculated like how strong the cable needed to be for the weight of the people, but not the centripetal acceleration, like the centrifugal force of the people.
Also, it's that.
Yeah. Right where kinetic energy is the highest, right? Right where ML theta dot squared is biggest. It just snaps and they go flying off.
I mean, at least it was somewhat safe. They're not like 40 feet above the water.
I guess so, yeah.
That must have been fun. I mean, that's like a second. Yeah, that'd be really fun.
I think it was, I think somebody got knocked out. Yeah, you don't want to hit the water that fast, uncontrolled, strapped to other people. Like it was not,
Yeah, so get it right this time.
not a well thought out plan. But anyway, we could figure out, we could get the real answer for how strong the cable needs to be.
What you would do? I would go, you just need like a couple of lines of down a lot and wait.
So we figure out at the low end, it's like 79.5, high end 80.1. So for the most part, like kind of a constant, at least like the very, if we ignore every term except for the linear sine terms, all the linear terms, it would be a constant value, just MGL. But here, even for small angle, it bounces up and down. And then we could even say that tension nonlinear is still going to be M times G times L, and then plus. Oh wait, I left out that cosine term, huh? Do we want to leave that in for the linear one? I don't know, that's up to you. It should be small, but
David, it's recorded. I know, I just don't want to go back and watch.
and there, for small angle, we should see, like, tension is tension. There's no magic here. There's a little bit of there should be a difference if we ignore that cosine term. But again, it's not a huge difference. We're still hitting the same kind of max value because we're including that theta squared. But if we look at jumping off of a bridge, so initial angle is now 90. Things are different now because angles are large. What's your problem here? Oh, because I have that. Still have constant energy. But now we're starting to see like a difference in kinetic and like nonlinear and linear. Linear, like if you include the cosine term and that d theta squared term, it's a more conservative approach. So if they had done that, at least that calculation, then it would have been better. Things would have worked out a little better. But if you say cosine is basically 1 and d theta is basically 0, then yeah, they're right. It should be a constant. Oh. And it should be constant, but it's not. Big changes. We start off at 0 tension, then ramp up to 100. Hopefully make it back on the follow through. Yeah. All right. Oh, go ahead.
So when we reference like our tension and potential kinetic energy calculations, like how specific do you want us to get, like on a project? Like
More specific is better. So what do you mean?
well, because like I mean, I guess like we could go back and like write all that out, but like I don't quite know how to explain where like every little bit of that came from.
Yeah, and like if you want any of this, like you can have it. Yeah, and you can either take it off the video or I can share, like send these blocks of code to you or post them in an announcement or anything. Yeah, it's not meant to be like, oh no, now I have to learn Python. It's more like, all right, this is what I want to do. How do I get it? Like, can you show me how to just put that together? Yeah. Yeah, but if your goal is like, all right, let me compare like kinetic potential energies, then like make a plot and say like, hey, here's potential, here's kinetic, linear, nonlinear, and they're different. They have to be different. Yeah. Cool. Thanks. Thanks a lot.